In Search of Soil.
All right, so if we go back to your early days of first studying microbes at University of Missouri, why did you get into that field to begin with?
Well, I got into it originally. I was into soil science, and I got interested in soil science because I read a book called Empty Harvest by Bernard Jensen, which talks about sort of a depletion of trace minerals in the soil and how it impacts quality of food, and then therefore how it impacts human health. So I was really interested in that connection between soil and agricultural practices and the quality of the produce and human health. Um, I went to study that subject at the University of Missouri, and I was a little disappointed at the beginning because the curriculum and sort of the way of thinking was very chemical dominated, which is typical of big land grant universities that are strong agricultural schools. The state of Missouri, we have the headquarters of Monsanto in St. Louis. So of course they're a big contributor to the school. And just generally the way of thinking was this chemical approach, which is dominant in agriculture.
Eventually, you find yourself actually in Japan studying in Dr. Higa's lab. And what was that experience like studying under him?
Oh, it was amazing. He had a lab of about uh, eight students, several international students, and all doing Masters of Science in bioproduction. And because of the international sort of even back then, the international use and work going on with these concepts that Dr. Higa originally put forth in his books, because it was happening all over the world, he was often invited. And so I did a lot of traveling with him around the world, and did some translation for some of his meetings and presentations. And yeah, it was amazing. He's incredible sort of visionary and scientist, and understanding how to use microbes.
If you go back to those days studying under him in the lab, what were some things that you guys were working on that were showing, really promising or outstanding results?
Some of the work that was most exciting at the time was or two subjects really that come to mind. One is showing an effect or seeing an effect of increasing the overall diversity index in a system, in a soil or in an agricultural ecosystem. And a diversity index is like a way of measuring the amount of diversity and the level of activity of the biology in a system. And so we saw very significant. It was like in the chemical system, you have this trend over years. Okay, these are long-term trends, but in the chemical dominated system, you have this trend of reducing the diversity index over time. So you have less diversity, you have less activity of the biology over time. And with this tool of EM cultures, we think we saw that we saw back then that you can reverse that trend. So you can actually see and measure an increase in the diversity over time. And to me, that's like really, really fundamental with what's happening, around the world with the ecosystems. So that was, that was made a big impression. And then the other one was just seeing the nutrient levels. So, in a plant's growth cycle, it needs certain nutrients at different times. Like it might need more nitrogen during the vegetative stage, for example. And what we saw was that in the soils that had higher populations and activity of these beneficial microbes that we were adding and that we were measuring with EM practices, those basically the plants create some sort of message. What we saw was that the microbes would increase, for example, the nitrogen in the rhizosphere around the roots at the time when the plant needed increased nitrogen. So we saw a clear communication happening between the plant and the microbial community where they were symbiotic. They were both helping each other in some way. And we saw that through NPK levels over the growth cycle in the plant as well as in the soil with different types of treatments. So that was, really impressive as well.
And to set some terminology straight here, because I know this is where a lot of people get confused. EM, what is it?
So EM technically stands for efficient microbes. That's the proper translation from Japanese. In Japanese, it's Yuyo Bisebutsu, which basically means efficient microorganisms. When it was translated, when Dr. Higa's book was translated, it was mistranslated to be effective microbes or microorganisms. It's a small nuance, but efficient versus effective is it's different. So yeah, efficient microbes is basically this concept of having cultures or using cultures that have three main groups: the phototrophic bacteria, the yeast, and the lactic acid bacteria. Doesn't have only those groups, but those are kind of the three main groups. And that's really the concept. I mean, Dr. Higa came up with that concept. He actually started in the 70s working on it, and he figured out and had kind of the first EM culture in like 80, 81, and started testing that in soils. So yeah, EM is efficient microbes, and it's mainly a consortia culture of those groups, but not only those groups. Now, I would also say that there's an organization started by some of Dr. Higa's students, a company based in Okinawa called EM Research Organization, and they have since trademarked EM and EM1 as brands. So our company, SCD Probiotics, we don't use EM terminology really anymore. I mean, for me, mentally, it's still kind of this concept rather than a specific brand and product from a specific company. But yeah, that's so now EM is more like a brand from a specific company. And yeah, that's sort of the origin of EM terminology.
If we think about that concept, consortia, can you talk about that? because I think this is where some people get lost. They might make a lactobacillus solution and say, well, I know this is trade name and trademark now, but they say, I've now made EM. What are they missing?
Well, they may have made EM. I mean, if it's only lactobacillus or lactic acid bacteria, then yeah, it's not EM by definition, because it needs to have those different components. I mean, I think in the literature, EM is pretty well defined to have those three groups. There can be different population levels, different strains, but sort of generically speaking, if it's got all those groups, then you could call it an EM culture, from my point of view.
A lot of when I do the reading on EM, the consortia concept promises or implies this: the whole is greater than the sum of the parts. So if I just add LAB, if I add PNSB and I add yeast to the soil, or I have those minerals acting on their own, they would behave differently if I put them all together in one solution and apply that. What are your thoughts on that?
Well, I think you said it well when you talk about the sum is greater than the individual parts. If you just throw the organisms together, mix them up, it doesn't really work. It's not that simple. There is a culturing process where the way we do it, we actually create a number of different consortia seeds cultures, and then those seed cultures get combined into make a mother culture, but they don't all get combined at once. There's different stages of the fermentation and the development of it. The thing is that I've seen all this do-it-yourself stuff, including like the methods out of Korea, where you ferment the rice in the woods, in the soil. The problem with all those is that they're just inconsistent, and there's not really science. You've got to have some basic microbiology, and measure what's there and its stability, and including biochemical components. So it's very complex, and if for a user, like, there are plenty of great cultures where you can just buy a mother culture to do fermentation. So I wouldn't recommend trying to like recreate the wheel and make your own culture and stuff like that. It's not that simple, and you'd have to have pretty sophisticated lab and equipment to be able to have any success with it.
It's part of the problem in the homemades, whether it's the rice wash solution or rice in the forest capturing those microbes, is you don't know what you're getting. You could be breeding out good with bad.
Yeah, that is the problem. It's not produced using quality control measures according to material specifications. So you don't know what you're getting. And actually, similar with compost tea. In fact, there's been some problems with compost tea because in that when you aerate, you can get really nasty microbes, pathogens growing. And with the consortia culture, one of the attributes is the low pH, and that low pH really inhibits the undesirable or the disease-causing microbes to proliferate.
So you're creating an EM solution in a anaerobic environment lower the pH, and then you take that and you add it to an environment that is closer to a neutral pH and aerobic. How does that work at the end of the day? Anaerobic, acidic, now applied to aerobic, neutral. Do they survive? Like, what's happening in that transition?
Well, first of all, a little bit of technical terminology. You've got anaerobic and aerobic microbes, but then you've also got facultative anaerobes and facultative aerobes. And the microbes in EM cultures are facultative. So I don't know if I should be more technical on what those mean. Okay, well, first of all, it's not produced anaerobically. It's technically semi-anaerobic. Okay, there's still oxygen present. And the microbes are not obligate anaerobes. Obligate anaerobes means that they are killed by the presence of oxygen. Facultative anaerobes means that the presence of oxygen doesn't kill them. It's just they prefer there not to be oxygen. They grow better in the absence of oxygen, but they're not killed by oxygen. So they're facultative anaerobes. Yeah, and maybe that clears it up right there. The other question about pH is actually, if you add, like, pH is one measure, but then there's also the acidity and how buffered it is. So if you add like an EM culture, like a mother culture, which is let's say a 3.5 pH at a rate of 5% of, so 5 parts mother culture and 95 parts neutral water at a 7.0 pH. You'll see the pH of that water come down significantly. So maybe as low as 4.0 or 4.5. So yeah.
But then aren't the microbes used to surviving then at that low pH? But now I apply that even diluted down, higher pH water solution to my soil, and now it's getting diluted down infinitely times more. So they're existing now, and those microbes are in the water in the soil matrix. Are they, if they were used to being in that acidic environment when they're cultured out, how are they now surviving in a soil where if you just take a random soil sample, it's closer to neutral?
Yeah, I see your question. So you mentioned that they prefer the lower pH, but that's not actually true. The low pH is created by their metabolites, their waste, the cell's waste. Okay, it's organic acids that lower the pH. And when the pH gets low enough, different strains of microbes have different tolerance to pH, but generally the lower you get, the less tolerance there is. So low pH will kill, some amount of microbes, and in particular, it happens to kill pathogens more than beneficials, which is why you have like the low acid canned food laws, where if something is pickled and it's below 4.2 pH, it's pretty well preserved. It's not going to be harboring pathogens, and you can put it on the shelf and eat it 6 months later, and it's fine because of the pH. So the FDA has a whole category called low acid canned food, which is if the pH is below 4.2, I think it's 4.2 pH, then it's basically considered preserved, and it's fine to have a longer shelf life. So it's kind of like with alcohol, okay? Making wine, fermenting, the yeast produces alcohol. When the alcohol concentration gets high enough, it kills the yeast that produced it. Same
So,
thing with lactic acid producing bacteria. If that acid gets strong enough, and depending on the strain, it'll die, or it'll reduce in population.
so the acidic environment is the byproduct of those microbes, not the required condition to have those microbes live.
Correct.
So when you then apply them to a soil, they can go on living because they weren't bred to live in that acidic environment.
Yes. But I view it, not as much about this particular strain is going to go on to live in a certain population in the soil. It's more about you're going to stimulate the biology in the soil. So you're going to get an increase in beneficial organisms activity. So, it's like in our science, and especially the chemical approach, which is kind of how we were all raised. It's actually kind of simple because you can break it down into very specific measured components. Like the whole chemical industry and all the laws around it are designed for exactness. And we run into this importing and exporting microbes and cultures all over the world in our business because the laws were set up to deal with chemicals, not complex biology. So even when we take that sort of paradigm and apply it to microbiology, we like to isolate an organism and study it in the lab, and we can see what does it eat and what does it excrete, and subject it to different conditions and see what happens, which is great to study that strain. But the reality is that nowhere in nature does a strain ever exist in isolation, in pure culture. It doesn't exist. It's a man-made phenomenon. So, and turns out when you grow that organism that's isolated in the presence of other organisms, its metabolism is totally different. So I'll give you an example. Purple non-sulfur bacteria can fix nitrogen out of the air and put it into organic molecules, okay, and excrete those molecules. If you grow purple non-sulfur bacteria like Rhodopseudomonas spheroides in pure culture and measure its production of, its production of organic molecules with nitrogen, it has a certain rate at which it can do that. If you give it the same conditions and you add a Lactobacillus culture to it, the rate at nitrogen fixation triples. It goes a lot faster. And that's partially because of what the metabolites that the lactic acid bacteria are producing. So my point here is that it's very complex, and when you try to break it down in the lab to really understand it in isolation, it no longer represents what you're looking at, because that isolated culture doesn't really exist in the real world.
Well, I'm glad you said that, because I mean that echoes something that Dr. Paul Zorner said when I had him on. You put one microbe in the lab and you try and monitor what it does, and then you suddenly add other soil microbes with it, and you see different results. And is this how Dr. Higa came up with that original mother culture? Is this what makes it special? I think this is really getting at the heart of it. You don't just have three individual things that just would do whatever they do by themselves in the same bottle. You've put them in there, and they've been selected to be in there because now you get this circular ring of mutually synergistic behavior where the presence of one enhances the performance of another, and it closes that loop. So you end up with something that, like you said, if you isolated those three out, you wouldn't get the same results as if you put them together. And that's why that mother culture is so powerful, being what it is it's the three that are made and thriving to work together.
Yeah, and it's not only the three. That's maybe something that gets overlooked or misunderstood. And I'm not going to really go into much detail because it is proprietary, but that there's more than those three. And it doesn't start with sterile media. So the EM culture, like the mother culture, it's a culture starter, and it will cause the fermentation to go in a certain direction, and it will lower the pH and produce these metabolites that are inhibiting disease microbes. So, but it's not inhibiting other microbes that are on the substrates, and in lactic acid bacteria or phototrophic bacteria or yeast will also be on the substrates. So you're going to get some of those wild strains in the culture as well. So you really have a very diverse culture, okay, which by definition has to contain certain levels of lactic acid bacteria, yeast, and phototrophic bacteria, but not only those. It's not only those.
I love what you're saying. And now I'm thinking, okay, I'm a grower, I'm a farmer listening to this. I want to add EM to my soil, but I also have all this local microbes in my soil, whether I'm in California, New York, Kansas, or Florida. What is EM going to do to what I have locally?
Yeah, I think of it as a stimulant. It's going to stimulate that the beneficials in that system, and those beneficials, that biology in the system, when it gets stimulated, it's going to produce more good stuff that the plants need, including plant hormones, chelated minerals, plant available nutrients. It's also going to be pushing out those undesirable microbes, which they're undesirable because their metabolites, what they excrete, are oxidative or toxic to plant cells. And that's why they're pathogens, or that's why they're undesirable, is because what they produce hurts the plants. Whereas beneficials, the way I define it, a beneficial excretes building blocks of healthy cells in plants or animals. So vitamins, antioxidants, organic acids, healthy building blocks for cells. So yeah, I think of it more of as a stimulant to the system, but I also recognize that, and this may go back to what you said earlier about why hasn't it been adopted widely, and that is that it does take time, and it takes a consistent approach. Whereas our mentality is like we apply the chemical and we see the result within days or weeks. This is a stimulating the biology in a very complex system over time. It takes time, but what you can see over time is a shifting of some of those parameters that you can measure, which relate back to the health of the system. So Dr. Higa and Dr. Parr, who was with the USDA, wrote an article about classifying soils based on what microbes were dominant in the system. And there's basically 4 classes. Like one type of soil, which is very commonly associated with heavy chemical use over decades of using chemicals, pesticides, is what's called as a disease-inducing soil. So a disease-inducing soil, if you look at kind of broadly what kind of microbes dominate in that system, there's a lot of pathogens. So if you don't use the pesticides to keep the pathogen levels down, there's a lot of disease in your crop. That's a disease-inducing soil. On the other spectrum, there's a zymogenic soil, and that's a soil that is like high levels of beneficial microbes producing all the nutrients for healthy plants, maximizing what the plant needs, and low incidence of disease-causing microbes. So there's 2 classes in the middle, but what you can do is you can move a soil to that zymogenic state, and that's what you want to be at, because in the zymogenic state, you need less fertilizer and less pesticides, and you get healthier and more productive plants.
In terms of a long-term approach, like, I'm with you. When people hear long-term, if somebody was to go down the EM path, mother culture path, and apply this to a soil, to see long-term, significant, meaningful change, is this a year's approach?
It is, generally speaking, a multi-year approach, but you can see results within the first year, depending on what kind of system you're dealing with. And that's another challenge, right? You've got different climates, different soils, different crops, different management practices, maybe with pesticides or without. Or most are with pesticides, right? If it's conventional farming. But you can definitely see results in one cycle. Mm-hmm. But you're not going to see maximum results in one cycle. So now I will say, though, that our approach at SCD Probiotics, we've developed applications that are more like the chemical approach. So basically biochemical products from fermentation that act like chemicals. So I'll give you an example. In herbicide applications, all herbicides get applied with an adjuvant, typically a non-ionic surfactant. A non-ionic surfactant is a petroleum-based, petrochemical that reduces the surface tension of water and helps penetration of the active ingredient like glyphosate, for example. We now are we came out with a product called Probiotic, which is fermentation based, from all food grade materials and organic materials and with probiotics, and that is used to replace the non-ionic surfactant component of the herbicide. We're kind of talking about the basic stuff that we did 10, 15 years ago, but now we've taken the technology. I mean, the number of applications and products and mother cultures and biochemical byproducts that we have now based on this technology platform it's over 100 different products. We break our business into 3 different segments. One is industrial, another is agriculture, and then the third is consumer products. And so just to give you kind of an idea, in the industrial segment, we're replacing petrochemicals with bio-based biochemicals from fermentation in textile manufacture, leather manufacture, paper manufacture, as an example. And our goal is to basically replace petrochemicals with bio-based materials that are less toxic and have a better environmental footprint, less carbon footprint. So that's our industrial segment. And then our consumer segment is like, we've got dietary supplements, which are basically probiotics, but consortia-based probiotics. Your typical probiotic is like a pure culture probiotic that if it has multiple species, they were blended at packaging. Those organisms have never lived in the presence of other organisms. So it's that pure culture approach. But we also have come out with probiotic cleaning products. Of course, we've got lawn care, lawn and garden products. So all based on, this fermentation and where I started, which is this EM culturing technology of consortia culturing with phototrophic bacteria and yeast and lactic acid bacteria. And then in agriculture, we've got kind of your typical, we've got the bioag mother culture, which is a mother culture for making an activation for sort of general on-farm use. And we have quite a few farmers that do that on a very large scale. They buy mother culture from us. We send it to them in a 1 ton IBC, liquid tank. And then they use that it's called activation, or basically to make a fermentation and multiply it 20 times in volume. And then that becomes their concentrate, which they use for on-farm applications.
Right.
But we also have this line of basically biochemical products, which are in ag applications designed to replace the pesticides and the petrochemicals.
So the ones that are the mother cultures, one thing I think people miss on this is they say, oh, it's expensive. But you could buy a gallon of it, culture it out, like 20 times, and it comes down to cents per application. Can you talk a little bit about that? Because that's a key point I think a lot of people miss.
Yeah. So you said it. I mean, a mother culture, it can be used directly, but if you want to do it economically, then you can do 1 part of mother culture with 1 part molasses and 20 parts water and do a fermentation that's fairly simple, but also very predictable what kind of results you'll get. So like if you buy a liter for $30 of mother culture, and then you can turn it into 20 liters of mother culture, then it means it costs you $1.50 per liter of finished product.
Right. And I'm looking at your page here. So for somebody in ag or gardening, SCD, the bioag, would be the product you'd recommend people start with?
Yes.
And what's a typical...
I also recommend the kitchen composter, or the bokashi composter, because that's it's a really easy way to recycle your food waste into your garden. And it's pretty convenient, and it also kind of introduces people to fermentation, which that's one of the things where, like, going back to sort of the roots of this with Dr. Higa, in Okinawa, Japan, and Japan in general, and Korea as well, there's this, actually all over the world in certain ways, there's this practice of fermentation for food, right? Miso, kimchi, cheese, yogurt, sauerkraut. And the thing that Dr. Higa observed in Japan, they also do fermentation to feed the soil. There's some techniques and traditions where it's fermentation not just to feed your family or to feed your livestock, but to also feed the soil. and to grow plants. And so, he started looking at that, but from the traditional approach, like farmers who had been doing fermentation for hundreds of years to feed their soil, no microbiology, just the practice and the tradition. Those cultures, though, being passed down because those fermentation and those cultures are maintained. So, he started looking at that as because he was in search of an alternative to the chemical approach, because he saw the side effects and the toxicity that can come from the chemicals. And so he was looking for a way to use nature to reduce the chemicals. And that, what we do in our business is really true to that today. I mean, we've brought that concept and applied science and applied, millions of dollars and research and development but starting with that concept of these consortia fermentation cultures, can create all kinds of useful, beneficial products, both biochemical as well as live microbial or biological.
What are your thoughts on using these products as foliar feeds? Is there any benefit to that, or is it all straight to soil?
No, I think definitely foliar feeds is an important application. There's a lot going on the phyllosphere of plants. There's definitely a microbial community there. And so, what you don't want is pathogens dominating on the phyllosphere of plants. You'll get disease and stress to the plant from those pathogens. So having beneficial microbes and their metabolites on the surfaces of plants is one benefit from a foliar feed. And, I'm not really up to speed on the science of how much nutrients are absorbed through the phyllosphere, but I think it's still material or significant. So yeah, I definitely would recommend foliar feeds.
One thing you talked about is beneficial microbes push out pathogenic microbes. Is that, by push out, does that mean outcompete, prey upon, or alter conditions so pathogenic microbes can't survive, or all the above?
It's all the above. I mean, I have to be careful and make the disclaimer that, we're not making pesticidal claims with our products. And according to the EPA, if you make a claim that you affect the metabolism of another organism, then by definition, it's a pesticide. So claims about competitive exclusion can't really be made with a product unless you're going to get a pesticide registration. But the concept of competitive exclusion is basically that within a system, okay, whether it's a soil or it's the rhizosphere or the phyllosphere or the surface, a countertop surface in your home or the surface of your skin, there's in ecological terms, there's what's known as a niche and a carrying capacity. And it basically means that within a defined space or niche, there's a certain amount of life that will be there, that will be supported by that, by space, by air, by moisture, other types of nutrient compounds are there. And, a microbial cell doesn't need a lot. It can sit there dormant, doing nothing for, years, actually. So everything's got this niche and this carrying capacity. Now, if you put certain microbes there on a regular basis, you're going to influence which microbes are living there because it can only support so many microbes. So let's say a particular niche can support 100 cells of microbes. Well, if you put 90 cells there that are these beneficials, then there's only space for 10 cells of pathogens, just using a simple example.
When I apply a mother culture, like the bioag or something, a lot of the worry that people have is I'm going to pour it on and like, I don't know if it's going to live or die. What can you say to give me some cause to relax on that? You know, because I think the worry is I'm going to apply it, but there's already like local microbiome there that's thriving. And it could be like, I'm dropping these new guys in and they're just like, nope, not coming in here, not setting up shop. Like, we're dominating. And then you've just poured it on and they like it best become food for other microbes. What are your thoughts on that?
I mean, the best thing is to measure what qualities are you measuring, or what qualities of the system are you observing or measuring, and those are where you should look to see the benefits of using these types of cultures. So if you're seeing, what you should expect to see is changes in the physical structure of the soil, improvements in the cation exchange capacity of the soil, decreases in undesirable microbes, increases in beneficial microbes. All those are all things that you can see, that you can measure, but you really see it in the health of your crop, or maybe in the health of the soil. You can observe it. So it kind of doesn't matter whether it's happening because the microbes survived, or because they fed something, or some metabolite stimulated the system. It really doesn't matter if you're getting the benefits that you can measure and see in terms of productivity, yield, that type of thing.
One thing I do want to make sure we cover in this is, if we look at the three main groups, and I know you've emphasized there's more than three, but if we look at the three main kind of by definition groups in that mother culture, let's go through them. So we have Lactobacillus, Phototrophic bacteria, and yeast. Can you talk about each one specifically and its role in the soil? So if I just add Lactobacillus to the soil, what is that doing for the soil and the plants in that soil? And then just going down the list.
Well, all three of them produce different types of substances that are beneficial to plants, like plant hormones or plant available nutrients, or they produce substances, metabolites, that interact with the nutrients in the soil to make them plant available. And then they don't produce things that stress the plants, which is what pathogens do produce. So, they each have different types of things they produce in those broad categories. Like phototrophic bacteria produce antioxidants, and they also can engage the nitrogen cycle. They can fix nitrogen out of the air, for example. Lactic acid bacteria produce organic acids, which have a benefit for the area around the rhizosphere. Yeast produce vitamins and chelating materials. So, but it may not be that those things they produce are being directly absorbed by the plant. It could be that they're stimulating that biology, so the overall activity increases, but increases in a certain way that's beneficial, rather than pathogens that are producing stress compounds.
Would that be the case for adding a mother culture to a traditional compost pile? Lactobacillus isn't going to break down lignin in wood, but it might produce byproducts that feed the fungi that break down the wood.
Yeah, exactly. We do a lot of composting, inoculants, and projects, and yes, one is accelerating the process. It absolutely, you can measure the acceleration of the process, making it more uniform so that you're getting a more consistent finished product, which is important in commercial composting where the end product's being used for fertilizer. So the beneficial microbes going in a fermentative or regenerative pathway versus putrefactive pathway. So disease microbes are defined as disease microbes because they secrete or they excrete metabolites that are stressful to plants and animals, that oxidize the cells and damage the plant. So it just so happens that those types of organisms also produce foul smells. A lot of those metabolites are odor compounds. So it's like we have God-given built into us the ability to tell if something is bad because it's putrefied and it smells bad. If you grow E. coli in the lab, for example, it stinks. Okay. So with the regenerative pathway, the beneficial microbes, it doesn't stink. It's more of a sweet fermented smell, a pickling smell, and it doesn't linger and it doesn't go long distances. It's there, but it kind of goes away. Whereas a stinky one, like if you go to a place where there's high levels of foul odor compounds in the air, like maybe on a livestock barn or a wastewater treatment sludge handling plant, like that stuff sticks to your clothes. Like you leave that place and you gotta change
Right.
because it still smells. So that's just, so in composting, odor control, we have some clients that are like doing large scale composting near urban areas and they can't have a foul odor. They'll get shut down. So they use our product not only for accelerating the process, but also for controlling odors.
And the odor control is done effectively. Like if we look at the microbial side, it's just eliminating those or lessening the putrefying organisms that would create the odor to begin with.
That and there's also there's a chemical effect. So one effect for odor control is displacing the microbes that create odors. Another is odor compounds that already exist and neutralizing them instantaneously chemically. One is a biological process that can happen over time. The other is an immediate chemical reaction, which is neutralizing an odor compound.
Okay. Thinking ahead, somebody goes down a program of regenerative ag and really changes their microbial makeup in their soil for the better through a product like yours and just good agricultural practices. Is there a way that you see that someone, and really I think this is how the community ultimately benefits at the end of the day, if this is possible, where I could take some of my healthy soil and culture that out, use that to seed microbiology at another part of the farm, at the neighbor's farm? Because eventually, like, I'm just thinking, I apply your stuff and it's great that I'm buying this consortia from you, but a lot of the benefit I'm getting is local to me because that consortia is stimulating what I have. Is there a way for me to now share this built up microbial base?
Theoretically, yes. I don't know that it's the cost benefit is there, to do it that way. And there's also risks because you're not eliminating pathogens in your system. Like there's still pathogens in your soil. In fact, one of the things that Dr. Higa used to say in like microbiology 101 class was, it's not the presence of a pathogen that causes a problem. It's the high population of the pathogen. And in fact, pathogens in low population are actually beneficial because they stimulate the immune response. So you don't actually want to get rid of all the pathogens. You want there to be low levels of pathogens because that actually stimulates the immune response. You don't want those populations to get so high that you get the symptoms of disease. That means there's an imbalance and this organism is too high. So with that understanding, if you take that to culturing your soil or your compost or those practices, there's some risk that you end up growing and proliferating something that you don't want to, unless you have some sophisticated microbiology lab capabilities. But I feel like that's really what like the value proposition for our business with mother cultures is that we provide a reasonably priced product that is consistent and quality controlled. And when you use it to start a fermentation, you're going to get consistent results. You're going to get the production of those beneficial microbes and their metabolites. And yeah, can you do it on your own? Like you're saying, theoretically, I probably, but I don't know that that's really practical.
Is there an overboard? Can I say I'm on a farm that requires 100% irrigation, and every time I irrigate, some of that mother culture is going out in the line. Could that be a problem?
No, I mean, it's self-limiting. I mean, yes, too much of a good thing is a bad thing, right? You can, like, for example, a plant that's highly sensitive to pH, if you poured mother culture straight on its roots, you would probably damage it because of the acidity. But those are all not really practical situations. Like a farmer or a gardener, they don't want to use too much. Like why put it on straight? Why overdo it? So yeah, I mean, I believe in too much of a good thing is a bad thing concept, but from a practical point of view, we never see it. We never see like, oh, I added too much and therefore, I have a damage in the system. It's somewhat limiting, again, because of that niche and carrying capacity concept. If you use too much, then yeah, more will die off and you won't get the benefit of having used double the amount, for example.
So just to sum this all up, I mean, is the whole gist here really, we're in a world that's became microbially depleted, and using a mother culture like the one you produce is one tool to help reseed and repopulate microbes in these depressed microbial populations around the world.
Yes, I would say it slightly differently in that I wouldn't say we're in a microbially depleted world. I'd say that a lot of, this is a very general statement, first of all, right? But a lot of this ecosystems, especially farming systems, are they're stressed or they're depleted or they're worn out or they have high chemical residues built up. And using a mother culture, using a product like ours, it stimulates the beneficial ecology of that system. So I see it more as a stimulant rather than like a microbial inoculant.
Hi, everybody. Thanks for watching. Subscribe here to get the latest from the show. Also, be sure to check out some of the great clips and watch the full interviews right here on In Search of Soil.